Let's look at confidence intervals for proportions. Suppose we have two main candidates running for President of the United States, like John F. Kennedy versus Richard Nixon. This is their 1960 debate. Or how about Donald Trump versus Hillary Clinton? They ran against each other in 2016. Believe it or not, Donald Trump invited Bill and Hillary Clinton to his wedding to Melania. Oh, those were happier times, less bad blood between them. Or suppose we have Kanye West and Taylor Swift running against each other for president. Okay, suppose we have two main candidates running for president of the United States, Kanye West and Taylor Swift. It's the week before the election. Obviously, we don't know the proportion of likely voters who plan to vote for Taylor Swift, but we want to estimate it. So we randomly select 1,000 likely voters and survey them. In this case, what is the population? What is the sample? Okay, the population is all likely voters, and the sample is the 1,000 likely voters that we survey. What does P represent? P, recall, represents the proportion of likely voters in the population who plan to vote for Taylor Swift. We don't know that. What does P hat represent? It represents the proportion of likely voters in our survey who plan to vote for Taylor Swift. It's an estimate of P. P hat is called the point estimate. Okay, we select 1,000 likely voters and ask them whom they plan to vote for. 475 say they plan to vote for Taylor Swift. Find a 95% confidence interval for P, the proportion of likely voters in the population who plan to vote for Taylor Swift. What do we mean by a 95% confidence interval for P? We don't know the value of P, the population proportion, but we can estimate it by using P hat, the sample proportion. We want to be able to say that we are 95% confident that P is in a certain interval. Let's find such an interval. Okay, here's what our normal distribution looks like. Recall that. Okay, when a variable has a normal distribution, a 95% confidence interval would be the mean minus 2 standard deviations and the mean plus 2 standard deviations. According to the central limit theorem, P hat, the proportion of successes in the sample, has mean P and standard deviation square root P times 1 minus P over n. Sometimes we call this the standard error of P hat, or SE of P hat. And the distribution of P hat approaches a normal distribution as n approaches infinity. Okay, I don't want to get too deep in the weeds here. The point is that the endpoints of a 95% confidence interval for P would be mu plus or minus 2 sigma. In this case, it would be P hat plus or minus 2 square root P hat, 1 minus P hat over n. That's the key thing you need to remember here. Now, we don't actually use 2. 2 is okay as an approximation. Really, it's more 1.96. So we want P hat plus or minus 1.96 times the square root of P hat 1 minus P hat over n. Those are going to be the endpoints of our confidence interval. Okay, so to use this formula, we must have NP is greater than 5. That's the expected number of successes. And NQ, or n times 1 minus P, sometimes we call it NQ, n times 1 minus P is greater than or equal to 5. Otherwise, P hat may not be normally distributed. So NP and n times 1 minus P, both of those have to be greater than or equal to 5. So here we've got it. Here's our formula. Let's plug in what we know. P hat, that's the estimate of P. It's 475 divided by 1,000, 0.475. Because of the 1,000 people we surveyed, 475 say they plan to vote for Taylor Swift. So that's P hat. We've got 1.96. P hat is over here. 1 minus P hat is over here. N, number of people in the sample, is there. So when we grind this out, we end up with 0.475 plus or minus 1.96 times 0.01579. And 0.475 plus or minus 1.96, 0.01579 is roughly 0.475 plus or minus 0.031. So a 95% confidence interval is going to be 0.475 minus 0.031, which is 0.444, and 0.475 plus 0.031, which is 0.506. Okay, so we're 95% certain that the true value of P, the population proportion, is going to be in this interval. The margin of error is 0.031, so it's this quantity here, which is really the same as this stuff over here, 1.96 times that square root expression. That's the margin of error. So find a 90% confidence interval for P, the proportion of likely voters in the population plan to vote for Taylor Swift. We did 95 a moment ago. Now let's do 90. So everything's going to be the same, except For 95% confidence interval, this number is 1.96. The endpoints of a 90% confidence interval would be p hat plus or minus 1.645 times square root of p hat 1 minus p hat over n. So in this case, everything's the same except we have 1.645 over here. That works out to be 0.475 plus or minus 1.645 times 0.01579. That's 0.475 plus or minus 0.026. So a 90% confidence interval for p is 0.449.501. Notice it's going to be a little smaller than the 95% confidence interval because we're only 90% confident that p is in that interval. In general, the endpoints of a confidence interval for p would be p hat plus or minus z star times the square root of p hat 1 minus p hat over n. And that's where z star can be found over here. So depending on what our confidence interval is, these are the values of z star that we want. What do we mean when we say that the endpoints of a 90% confidence interval for p are 0.449.501? There's a 90% chance that the actual value of p is in this interval. That's what we mean. What do we mean when we say that the margin of error is 2.6%? There's a high degree of certainty, in this case 90% certainty, that the actual value of p is within 2.6 percentage points of the estimate p hat. So going back to what we had over here, so again we had 47.5%, 0.475 plus or minus 0.026, 2.6 percentage points. That was our margin of error. How large does our sample have to be if we want the margin of error to be 1% with 90% confidence? Earlier, we saw that the margin of error, in other words, ME, is z star times the square root of p hat 1 minus p hat over n. If we rewrite this so that we have n in terms of ME, the margin of error, we have n equals z star squared p hat 1 minus p hat over ME, margin of error, squared. Okay, so let's plug in what we know. It's a 90% confidence interval, so z star is 1.645, p hat is 0.475, 1 minus p hat is 0.525, the margin of error is 0.01 because we want it to be 1%, and that turns out to be 6748.15. Now with these sample size calculations, we round up to the next integer. We don't round to the nearest integer, we always round up to the nearest to the next integer to play it safe. So we need 6,749 people. That's an enormous number of people. It would take a lot of money to survey such a large number of people. So that's why we don't usually have such a small margin of error of 1%. How large does the sample have to be if we want the margin of error to be 1% with 90% confidence, but we don't know p hat? See here, we could plug in p hat. What if we don't know p hat in advance? What if we have no idea what p hat is? Okay, so here's our formula for n. This is always going to be less than or equal to, so we got the z star squared over here, just like we've got over here. It turns out that p hat times 1 minus p hat is always going to be less than or equal to 1/4, regardless of what p hat is between 0 and 1. So we just rewrite our formula like this. We can put the 4 downstairs, and we've got z star squared over 4 times the margin of error squared. In other words, 1.645 squared over 4 times 0.01 squared, and that's 6,665.06. Again, we round up to the next integer, not the nearest integer, but the next integer to play it safe. So we'd need 6,766 people. The most common form of color blindness is red-green color blindness, where red and green look similar. It's much more common among men because it's found on the X chromosome, and women have 2 of those. So if you don't have red-green color blindness, you can see reds in here, you can see greens in here. If you do have red-green color blindness, then the picture on the left would look like this. You don't see red and green, just everything looks green. A 95% confidence interval for the proportion of German men who have red-green color blindness is 0.071, 0.083. I didn't make that up, that's an actual figure. So let's calculate a point estimate of the proportion of German men who have red-green color blindness. Well, the endpoints of a 95% confidence interval for p look like this. It's p hat plus or minus 1.96 square root p hat 1 minus p hat over n. Notice that the point estimate is always in the center of the interval. So at one endpoint you have p hat minus this stuff. At the other endpoint you have p hat plus this stuff. So smack dab in the middle, you're going to have p hat. So if we just average the endpoints of the confidence interval, we get p hat. So p hat is going to be 0.071 plus 0.083 over 2, in other words, 0.077. So that would be our point estimate for p. So in other words, we would, based on this confidence interval, we would estimate that 7.7% of German men have red-green color blindness. And that's actually pretty standard throughout Europe. It's color blindness, red-green color blindness is less common outside Europe, but in Europe, it's roughly 8%. Find the margin of error. Okay, we've seen the endpoints of a 95% confidence interval for p look like this. It's p hat plus or minus 1.96, p hat, square root p hat 1 minus p hat over n. And we saw that this is the margin of error, 1.96, square root p hat 1 minus p hat over n. So equivalently, it's the distance from p hat to an endpoint of the interval, because the interval is going to look like this. You have p hat plus this stuff, and you have p hat minus this stuff. So to figure out what this stuff is, we just need to look at the difference between one end of the interval, like 0.083, and the midpoints of the interval, 0.077. When you do that, you get 0.006. So this stuff over here, that's our margin of error. It's 0.006, or 0.6%. By the way, here's some famous people who have red-green color blindness: the wrestler and YouTuber Logan Paul, the writer Mark Twain, Mr. Rogers, Fred Rogers, rockers Rod Stewart and Neil Young, and Mark Zuckerberg.